formulas that we need to take care of to be able to solve more equations. Okay, more differential equations, the one that is going to involve more of the step functions. I just gave you the one that I gave you was not bad, that last one, but it can be a little bit more involved. In order to do it, there are two nice theorems that will take care of lots of those difficulty in finding the Laplace transform. Remember, we talked about one of the translation theorem, if you like, and that was the one that if you in the function f of t, if you replace the t by t minus c, then you are going to bring the unit step function. That was the Laplace of the upt f of t minus c. And that give you, enable you to find the Laplace of those step function. So what we're going to do, we are going to do it the other way around, because the variable that you change was t into the function. But when you find the Laplace of the given function, Laplace would be a function of s. So what we're going to do is we are going to get the translation for the s. We shift the s. We shift it to the right. If you shift it to the right like s minus a, then you have to pay for it. How we're going to change it, okay? And the change is going to be the following theorem, okay? So this is the kind of a second translation theorem, we call it. And it's so useful. Remember the other night, I tried a couple of problems for you. I was not able to continue. And it's going to be used when you want to find the Laplace inverse. When we get a rational expression, if the denominator is not factorable, you have to go through this method, okay? We have no other choice. So that's a great theorem. It's again part of 7.3. We talk about one of those translation theorems. Now we're going to give it the second one. So this is, we can call it second translation theorem or just a translation theorem. Translation theorem. In your book, refer to it as S translate or S shifting, but this is it. So the statement of the theorem is going to be if any a number is given to you, if a is any number, any real number, okay, then okay, this one. Then the situation that we're going to have is going to be the following version that the Laplace, Laplace of e to the at f of t is going to be f of s minus a. So this means if you want to shift the variable in the Laplace transform from s to the s minus a, shift it to the a, then what you have to do is you have to multiply the function by e to the at. So if you shift the s into the s minus 2, so your function would be e to the 2t f of t. Okay? So the way we write it down, or if you like, you say if you want to find the Laplace of this function, it's going to be quite a lot popular. This is the way we write it down. We say it's equal to the Laplace of f of t. Laplace of f of t, but when you change the s into the s minus a, that's easier to memorize. And when we apply it, this is the way we do it. So as soon as you see this coefficient, you can drop it. You can find the Laplace of f of t, but when you find it, you change the s into the s minus a. Very easy to prove. I can prove it for you. See the proof? Let's use the definition of a Laplace transform. So the definition is going to be what? What is the Laplace of e to the at f of t? Simply, it's going to be integral from 0 to positive infinity. Remember, e to the what? E to the negative st times the function. The function in question in this case is e to the at. E to the at f of t dt. We can call it g of t. definition of a Laplace of f of t is 0 to infinity e to the negative st ft dt. Now, if you simplify this one, you got it. 0 to positive infinity. You see the base are the same, so add the exponent together. So that gives a negative st plus at f of t dt. Now, this is going to be 0 to infinity. I want to write it down in the form of the Laplace transform. So it's going to be e to the factor of the negative sign, and negative t is going to be s minus a times t. And this is going to be f of t dt. Remember the definition of f of s? Just remind you. Note that. What is definition of f of s? F of s, which is the Laplace of f of t, is equal to the 0 to infinity e to the negative cs f of t dt. So if you compare them together, you see, compare these two together. This is like you change the s into the s minus a. So if you change the s into s minus a, if you shift it, so that would be f of s minus a, which is equal to the 0 to infinity e to the negative c s minus a f of t dt. See, that's it. Because the Laplace transform is a function of s. You change the s into the s minus a. So we go to the function wherever you see the s, you change it to the s minus a. So nicely proved. Okay. So that's it. Therefore, if we have the Laplace of e to the at f of t, just simply is going to be f of s minus f of s minus a. Very useful formula. We will see the way we're going to do it. So I can go back to those equations that we tried to solve with the other night. You can do it. But first we have to practice to see where we are going to use it. The Laplace transform, especially for the Laplace inverse. Any question? So if you translate this one, if you work on the s, you have to multiply the function by e to the at. And the one that we did the other night was if you change the t to the t minus c, then you have to bring the unit a step function to be able to do it. Okay? So to give you an example, the way we're going to apply it, this is it, example. The example is going to be, we want to evaluate, okay, evaluate each of the following Laplace transform. So the first one, that's it. We want to find the Laplace transform. Okay, the Laplace transform of t cubed e to the 5t. Okay, that's it. That's question. As soon as you see that coefficient of the e to the 5t, you know that you can do it by the, okay, by that shifting. So if you compare it with the formula that we have, you can rewrite it if you like. Rewrite it into the form of, you see you are interested in Laplace of, put the e to the 5t here. It's going to be e to the 5t, and then your function is t cubed. According to the formula that we talk about it, this is going to be equal to what? This is going to be equal to the Laplace of the function. The function is, you see, this is going to be your f of t. This is your f of t. So the result is going to be what? As we talk about it, is going to be lap f s, and s goes to the s minus a. So it's going to be Laplace of the function, which is a t cubed. And when you find it, the function will be function of s, but you're going to change the s into the s minus 5. F of s minus 5. Any question? What's the Laplace of t cubed? It's going to be a 3 factorial over s s to the 4th power. Yes, that's it. Okay, but you do it that we change the s into the s minus 5. Because this is going to be f of s, that you change it to the f of s minus 5. 3 factorial would be 6. Okay, you change the s into the s minus 5. So that give you s minus 5, everything to the, okay, everything to the fourth power. Okay, so this is going to be the final answer. So Laplace of t cubed e to the 5t is going to be equal to the 6 over s minus 5, everything to the 4. You see, the way you are going to use it, it's going to be the other way around. You try to solve a differential equation, you get this to this term. You don't have to break it into the, you know, like in calculus, s minus 5, s squared, that, no. You know that this is going to be there is going to be a translation. So you just go for it. Okay. So this is the first one. Any question? The more popular one is the next one that's coming in various differential equation. Okay, so as soon as you see this coefficient of the e to the at, you can do it by the translation here. Otherwise, it takes time. You see the one that it's otherwise written as c e to the. Okay, so this is the first one. The other part is going to be. Let's give you this one, number 2. Then we do the other way around. With the sine and the cosine, popular. Okay, number 2. You want to find the Laplace of, they give you something, you see, an exponential coefficient times cosine times sine. So in this case, you have e to the negative 2t, e to the negative 2t cosine of the 4t. You see, if you want to do this directly, you have to use go through the integration by parts, like in calculus 2, to be able to find it. Right? You can easily use this theorem. Again, you see this. So you work on the Laplace of the cosine of the 4t. And when you find it, you change the s into the what? A is a negative 2. You change the s into the s plus 2. And then you're done. Okay, so this is going to be the solution. Again, remember, this is going to be your function. This is going to be your f of t that you have to work on. So again, Laplace of e to the negative 2s cosine of the 4t is going to be equal to the Laplace of the function, Laplace of the cosine of the 4t. When you're done, you change the s into the s minus a. A is a negative 2. So it's going to be negative positive. S plus 2. Okay, what's the Laplace of cosine of 4t? It's going to be s over s squared plus 60. So what you have to do is you have to change the s into the, shift the s plus 2. So the final answer would be s plus 2 over s plus 2 all squared plus 16. Okay, so that would be the Laplace of, that is the Laplace of e to the negative 2s cosine of the 4t. Nice, nicely done. Okay, any question? So we did have a couple of these on that practice quiz that I drop it. It's going to be coming back when we get to the test. The one that I dropped the other night because we didn't have these theorems. Okay. Now the other way around, which is the one that you're going to use when you want to solve differential equation. Okay. How about Laplace inverse? So the second example is going to be, you want to evaluate this Laplace inverse. Okay. So let's go with this one. The one that we have is about, this is very popular. I'm going to give you 2. So this is the first one. Most of the time you arrive at this. S squared plus 6s plus 11. You see the denominator is a quadratic. So we try to factor it. So far, everything were factorable. But this is not going to be factorable. Okay? You cannot do it. So what you do, like the one that, use this type of things in calculus when you want to find the integral related to the tangent inverse. Okay, the procedure is the same thing. So what we're going to do, we are going to make it completing the square down the denominator. We change it to the u squared plus a squared, if you like. And you know how to do it. Okay, so the solution is going to be, I'll just remind you, that's it. This is 1 over s squared plus 6s plus 11. So it's going to be equal to the 1. So what you do, you divide this coefficient by 2. Okay, that gives you 3. So you are going to have s plus 3 all squared. And then you do s squared, s plus 3 squared is going to be s squared twice after first times second, which is 6. And it's going to be plus 3 squared, which is 9. You don't have the 9. So you subtract the 9. You see, it's the way we do it. Exactly now when you want to solve the quadratic equation or so very easy method. Divide this one by 2. Some people, they try to break the 11 into the 9 and the 2. You can do that one too, but this is easier. Divide this coefficient because this is twice after first time second when you get the perfect square. Okay, 6 divided by 2, that gives you 3. You get your second term, s plus 3 squared. But you see, one term is going to be 3 squared, which is 9. You then have the 9, subtract it. Okay, so this would be exactly the same thing. Combine the like terms together. So that gives you 1 over s plus 3 all squared plus 2. Now this is of the formula. If you call s plus 3, you see, call s plus 3 s. So it's 1 over s squared plus 2. 1 over s squared plus 2, you know that. If you can find the Laplace inverse of this one, which is the sign, then when you find it, you have to multiply by what? Multiply by the shifting that you have, the e part. So this is it. We go on, we find the Laplace inverse of this one first. Okay, so this is it. So you end up with 1 over s plus 3 squared plus 2. You just check to see if you are ready. Okay, if you change this one to the s squared, this is s squared plus 2. So you need the sign. In order to get the sign, you need a on the top. Remember, a is a radical 2. So we are not ready. So you better make it into what? 1 over radical 2. Laplace inverse of on the top to be radical 2. This is going to be s plus 3 all squared plus 2. So now it's going to be equal to what? It's going to be equal to the 1/2. You see, because of the shifting, you shifted the s into the s plus 3. So you need to have 1 e to the at. So e to the what? A is a -3. E to the -3. -3, the leftover. The leftover is a sine function. So the leftover is going to be sine of, okay, sine of what? Rad 2 of t. So this would be the Laplace inverse of the given one, 1 over s squared plus 6x plus 11. Okay, this is the way we do it. You may have to do it a couple of times when you want to solve a differential equation, because you will get this from now on. When you get your differential equation would have a repeated solution, or it's not going to be factorable. You get involved to this number right away. Okay, any question? So that's the sign. But what would happen if there is going to be an s on the top? That would be a little bit tricky. Okay, so that would be your second case. Okay, so what is let's, we can put an s on the top of this and check it. So how about Laplace inverse of this function? Put an s on the top, s. It will be the same one. You can switch it if you like. This is the one. Again, you try to factor the denominator. Okay, with this method, you don't need to use that factoring method at all if you are If you accepted the sine hyperbolic function, everything is done. Okay, but for the sum one, we just go with this. Okay, again, you have to take care of those denominator first. Okay, to see what's going on. So we already done that denominator part. So we are going to check it. So what's going to be the solution? Solution is that the Laplace inverse. So we change it. It is S. We already talked about it. So it's going to be S plus 3. S plus 3. All squared. Remember, plus 2 is the one that we did so far. Okay. So let's see what's the difficulty now. You see, you have to do it with the cosine. If you want to do it with the cosine is what? Is S over S squared plus A squared. But you're switching the S into the S plus 3. So everything must be consistent. So that S now is going to be S plus 3. So you have to create S plus 3 on the top. You see, you create S plus 3 on the top, then you drop it, you call it S. So in order to create S plus 3 on the top, for example, add and subtract. Okay. So this is going to be Laplace inverse. Okay, Laplace inverse of what? Okay, we write this one as S plus 3. We add subtract. Okay, that's one. Then this is going to be S plus 3 all squared plus 2. Okay. We create S plus 3 now. Now you have an extra term. That's a negative term. So what to do is we separate it. So it's going to be equal to the Laplace inverse. Okay, Laplace inverse of what? S plus 3 on the top. Then we get S plus 3 all squared. Okay, plus 2. Now it's going to be minus Laplace inverse of a new one. The top would be 3. Okay, and this is going to be S plus 3. We repeat it. A square plus 2. So it's going to be a little bit more to construct before going on. Okay, we are ready for the first part. We have S plus 3, S plus 3. We call it S square plus 2. So that would be cosine with the shifting. So this is going to be equal to, we shifted into S plus 3. So it's going to be E to the, okay, you get E to the negative 3t. E to the negative 3. And then the function is going to be cosine. Okay, is the cosine. Cosine of what? Root 2 of t. So that is the first one. That's the first one. Second one, you have to create the cosine, the sine for this. You pull out the 3, then as we did it for the other part, you need a radical 2 on the top to take care of the sine. So you're not ready. It's a minus. You can do it right away, we accept it. But I explain it again. Okay, that's a radical 2. So this is going to be L inverse. You have the radical 2 on the top now. And this is going to be S plus 3 all squared plus 2. Now we are ready for the sine. Okay, we are ready for the sine because we create, okay, we create the A over S squared plus 3 with the shifting. So the final answer is going to be the first one. We repeat it, E to the negative 3t. Okay, E to the negative 3 cosine of radical 2t. Now the leftover is going to be what? We have a negative 3 over radical 2. We have a shifting of E to the negative 3t again, but the function is going to be the sine. Sine of radical 2t, and then do that. Okay, so these are the operations that we are going to do quickly because we want to solve the equation. This is where we're going to use it. Okay, you will see automatically it's going to be coming together. And there is going to be S, and easily you will see that S on the top. But, we'll be fine. We'll be able to do it. Okay, so this is a format that we have. Okay, I have another one. I can do that one quickly too, but this is for this version. Okay, any question? So we are going to do it quite a lot later on. Okay, this is something very similar from your book. We can check this one too. Everything is already nicely given. Okay, nothing to worry about. So this is Laplace inverse of 2s. You see 2s plus 1, and that's s squared minus 2s plus 2. It's one of the equations that we solve to get to this one. Again, you check the denominator first. It's not factorable. It's not factorable. Okay, so you have to make a completing the square. So the solution is going to be, so I rewrite it 2s plus 1. To make it complete the square, you divide this coefficient by 2, so that gives you s minus 1 all squared, but you have to pay for it. Negative 1 squared would be 1, so it's going to be minus 1 and the plus 2. Okay? Because when you square it, this is twice of the first times second. So you are going to get a 2s plus 1. Now we get s minus 1 squared plus 1. Nice, 4. Now you are the shifting is s minus 1. So you have to create s minus 1 on the top. Okay, there are a different way to do it. There is a coefficient 2 over here. You can do it with the coefficient 2, or you can, break it. So this is one way to do it. This is s minus 1 squared plus 1. This is 2 times s, but we want it to be s minus 1. Okay, if you want it to be s minus 1, it's going to be what? It's a 2s minus 2 plus 2 plus 1. Okay, so we end up with 2 times s minus 1 plus 3. And the bottom one would be s minus 1 all squared plus 1. Okay, whatever you need, you just write it down, then you simplify it to find out, what's going to be the leftover. I put the s minus 1 here, so 2s minus 2. So I put the positive 2 to break it up. And now we know that we break it in 2 parts. So the part that we keep for the cosine, this is for the cosine, which we can call s minus 1s. So that's a 2s over s squared plus 1. Simply would be 2 cosine t. And the other part is going to be 3. And you have the s minus 1 all squared plus 1. Okay. So now the Laplace inverse of the original one, 2s plus 1 over s squared minus 2s plus 2. It's going to be Laplace inverse of the first one that we already talked about it. 2 is the coefficient. The shifting is e to the t, and the function is cosine of t. Okay, and the next one is going to be plus 3. Okay, this is going to be plus 3. The function is sine, and the shifting is 1 again. So 3e to the t sine of t, the final answer. Okay, so nice, can you find these method. Okay, any question? So that's the second translation theorem. Now we need to have one more. This last theorem that we're going to discuss is also very useful, and for solving the differential equation again. In your book, they call it derivatives of the Laplace transforms. If the Laplace transform is a function of s, you can differentiate it. You can find the first derivative, second derivative, etc. Okay, but that gives you a nice formula that we can apply in order to solve again the differential equation. Okay, so let's see. So this is going to be what is derivatives. Okay, derivatives of the Laplace transform, of the Laplace Laplace transform. Okay. I'm going to show you how easy it is. Then we can write it down as a theorem. Okay, there you are. So suppose we have the Laplace of f of t. It's given to you is equal to the fs, the function. If this is going to be the case, then the function is going to be what? F of s is integral from 0 to infinity. Okay, 0 to infinity, e to the negative st ft dt. Okay, if you want to differentiate it, you have to differentiate respect to the s. Okay, so differentiate both sides. Differentiate both sides with respect to the variable. Okay, of course, to the variable s. That's it. So the part to the left would be f prime of s. The part to the right, you are going to find the derivative with respect to the s of this integral. 0 to infinity, e to the negative st ft dt. Okay, so you integrate respect to the t, but outside you differentiate respect to the s. This is one theorem in calculus 3, or even in calculus 1, or calculus 2. So what you can do is, you can switch this. You can take the d over ds inside the integral, because the integral is integrated in respect to the t, so you're not going to do anything wrong. Okay, so it's going to be 0 to infinity. 0 to infinity, you differentiate with respect to the s of the function e to the negative st ft dt, like a partial derivative if you like. Okay, so what is going to be the derivative of this function with respect to the s? Any suggestion? Derivative.
Over.
That's it. It's not right. Okay. You missed something. Derivative with respect to the s. No. What's that?
Oh, negative t.
That's it.
Negative.
You see, you just differentiate e to the negative st respect to the s, not respect to the t. If you differentiate respect to the s, derivative u prime would be negative t on the top. Okay, so this is going to be 0 to infinity. You see, the derivative of e to the negative st, you know, the exponential function never change. Exponential function never change. You see, never change. F of t is just a constant, if you like. And you have to multiply by u prime. U prime derivative with respect to the s. Derivative with respect to the s of the top, negative st, derivative would be negative t. Negative t dt. Okay? So if you rewrite it, that gives you 0 to infinity. Okay, 0 to infinity. Then what we have? It's a negative e to the negative st. Put the t and f of t together. dt. Okay. So you can put it out. Pull out the negative sign here. So that gives 0 to infinity. E to the negative st. T f of t dt. Okay. So what would happen to this one? What is this in the terms of the Laplace transform? No, it's a Laplace transform of what? T f of t. T f of t, you can call it g of t. It's e to the st gt dt. So it's going to be Laplace of a gt. What is the gt? T f of t. You see the function inside? The function inside is this one. You can call it g of t. So 0 to infinity e to the negative st gt is the Laplace of g of t. So in this case, this is nothing but it's equal to the negative Laplace of t f of t. So that gives a nice result. The result is going to be what? Remember, we start with the f prime of s. That's f prime of s. That's f prime of s equal to the negative 1 Laplace of Laplace of f of t. To get these numbers, you can put the negative to the other side, and you have a formula. Laplace of t f of t is simply negative f prime of s. You see, nice formula. So this means if you have a Laplace of a sine t, you want to find the Laplace of a t sine t. The Laplace of a sine t is what? Is 1 over s squared plus 1. You differentiate 1 over s squared plus 1. You get the Laplace of t sine t. You see, Laplace of t f of t is going to be negative derivative of the Laplace of the function f of t. So you want to find the Laplace of t cosine t is going to be what? Negative Laplace of the what? Laplace derivative of the Laplace of the cosine. Okay, let's finish it. You get something better. Suppose you want to find the second derivative. It's easy if you can find it because the first derivative we have it. What's going to be the second derivative?
I don't think we actually want it. I think we'll find it.
T squared. For the first derivative, you get the t. For the second derivative, you get what? You get t squared. But this negative one would be positive because that is negative. You want to find the third derivative, the fourth, the fifth, the sixth, yeah. So you got it. So what is going to be the general formula? Oh, that's great formula. It's so useful when you want to solve the differential equation. So that's it. We can say safely, similarly, Laplace of t squared f of t would be the second derivative of a Laplace transform. And if you want to find the Laplace of the third one, just repeat that procedure. That gives you negative, the third derivative. So in general, this is it. If you want to find the Laplace of t to the n, f of t, it's going to be what? It may be positive or negative, so it depends. So it's going to be negative 1 to the n. The n derivative of the Laplace of a function. You see? Nice formula, so useful. So useful in application that you're going to have. Otherwise, you have to go with the integration by part forever, okay, to get these numbers. So with this true new one, there is nothing going to be no function that you won't be able to find the Laplace transform of those. Okay, and in one differential equation, you see all of them all over the places. So you quickly take care of it. Okay, we'll give you example. Any question? So that's it. The derivative. We are interested in this format because we are going to use it for the Laplace inverse in the formulas. Okay, so let's give you a couple of examples to see how we're going to apply it. Yes, question. You need the app that negative one. You know, it's true by induction. We can prove it. Okay, example. We want to evaluate a couple of these Laplace transform. Evaluate. Okay, how about this one? We want to evaluate the Laplace of t sine of the 5t. You see that's the one? Of course, one way to do it, the direct definition, integration by parts. I have to do it, but we want to use these formulas, of course. So the power of the t is 1. So you can use that formula for t equal to 1. So the way we're going to do it is going to be, you see, the solution. So you think about that f of t that we talk about it is going to be equal to the sine of the 5t. Okay. Sine of the 5t, then you have to find the Laplace transform of this function. So the Laplace transform would be what? F of s, it's a sine. It's going to be what? 5 s squared plus 25. So that's the original one. Now that you need the Laplace of t, just remind yourself, you are interested in the Laplace of a t, f of t. So your n equal to 1. So that give a negative f prime of s. So you have to find the f prime of s. Just apply the quotient rule to get it. Okay, so it's going to be equal to if of the top, bottom, bottom, top. If the top, bottom would be 0. If of the bottom times top. Okay, minus. If the bottom one would be 2s. So it's going to be minus 5 times 2s. Divided by the bottom square. S squared plus 25 all squared. Okay, so the Laplace transform of the t sine of the 5t. Okay, t sine of the 5t is going to be equal to, we have double negative, make it to positive. So it's going to be 10s. Okay, 10s over s squared plus 25 all squared. And then you're done. Okay. So this is the way we are going to operate. The one that we dropped the other night. Just bring it back now for you to explain it. And that was one t. That's a t sine. You can have more power. Let me just give you another one. So the one that we dropped the other night is this one. So you'll see them, in your next test. We want to find the Laplace of a t squared sine of the 2t. Again, you see the t squared, you realize that you have to do the derivative, but you have to use the second derivative now. Okay, so you set it up. This is going to be solution. So the function, again, f of t is equal to the sine of the 2t. You have to bring your f of s. Okay, we get the f of s. F of s is, in this case, is a, is going to be 2 over s squared plus 4. Okay. Now since you want the t squared, so the Laplace of t squared, f of t, is going to be second derivative. -1, you say -1 squared, at f double prime, which is going to be f double prime of s. So you have to differentiate twice. Okay, so we go for a f prime of s first. If of the top bottom would be 0, bottom top. Okay, so we get the bottom part is going to be 2s times it's going to be -4s. -4s divided by s squared plus 4 all squared. Okay, lift of the top times bottom 0, bottom top, -2s times 2 -4s. Yes. Now we want to find the second derivative. You can move it up. Just find the second derivative would be easier, or just the quotient rule as much. Okay, so I'm going to rewrite as a 4s times s squared plus 4 all squared, and I differentiate it again. So it's going to be f double prime of s to the -2. Yes, you are right. Okay, derivative of the first, -4 times s squared plus 4 to the -2. Okay, that's the derivative of the first. Second first, you know that the chain rule. -2 times -4s would be 8s, the chain rule, times s squared plus 4 to the -3 times the u prime, which is the 2s. Okay, derivative of u to the -2 is -2 u to the -3 times u prime. Okay, you just put these monomials together and then you're done. F double prime of S is going to be equal to is a -4 over S squared plus 4 all squared. Okay, and this is going to be plus 8 times 2, 16, 16 S squared over S squared plus 4. Okay, to the third power. So that give you the final answer. Okay. So that give you more tools to be able to find these Laplace, Laplace transform of the various function. And that's it. I give you example for the equation. Next time we have to check a couple of, or several equations to see how we're going to check these numbers.